Welcome, everyone. Today we are diving deep into Apache Spark to master structured streaming. If you want to process real-time data at scale, you're in the right place. Let's get started. Let's start with the what. What exactly is Spark structured streaming? Simply put, it is a highly scalable and fault-tolerant stream processing engine built directly on top of the Spark SQL engine. As a data engineer, the biggest conceptual leap you need to make is treating a live data stream as a continuously appending table. Every new piece of data that arrives is just a new row appended to this unbounded input table. The brilliance of this approach is the unified API. You can express your complex streaming aggregations and event time windows using the exact same dataset and data frame operations you already use for static batch data. Spark takes your batch-like query, figures out how to run it incrementally, and continuously updates the final result as new data flows in. It removes the heavy lifting of reasoning about streaming mechanics, letting you focus purely on business logic. Look at this flowchart to visualize the core paradigm. On the far left, we have our live data stream constantly generating events. Instead of dealing with complex stream operators, Spark simply takes these events and appends them as new rows into an unbounded input table. From there, the Spark SQL engine takes over. It runs incremental queries against this growing table and continuously updates the result table on the right. This abstraction is what makes structured streaming so powerful and easy to reason about. Now that we know what it is, why should you choose structured streaming over other frameworks? The primary reason is fault tolerance. In distributed systems, failures are guaranteed to happen. Structured streaming was designed from the ground up to deliver end-to-end exactly once semantics. It achieves this through a combination of replayable sources, checkpointing, write-ahead logs, and idempotent sinks. When a trigger fires, Spark records the exact offset range of the data being processed. If a node crashes, Spark simply restarts, reads the write-ahead log, and safely reprocesses the exact batch of data without creating duplicates in your downstream databases. Furthermore, because it sits on top of the Spark SQL engine, your streaming queries benefit from the exact same catalyst optimization and tungsten code generation that makes Spark batch jobs incredibly fast. You get rock-solid reliability combined with world-class performance. This diagram illustrates the fault tolerance architecture. Data flows from a replayable source, like Kafka, into the Spark execution engine. Notice the bidirectional arrow to the write-ahead logs and checkpoints. Before data is fully processed and committed to the sink, Spark saves its progress offsets here. If a failure occurs, Spark uses this checkpoint state to resume exactly where it left off, ensuring the idempotent sink receives the correct, unduplicated data. It's a bulletproof pipeline. Let's talk about how Spark executes your streaming queries under the hood. By default, structured streaming relies on a microbatch processing engine. It collects a small chunk of stream data and runs a fast batch job over it, achieving end-to-end latencies of around 100 milliseconds with exactly once guarantees. However, if your use case demands ultra-low latency, say, sub-millisecond reaction, Spark introduced continuous processing mode. This mode achieves roughly 1 millisecond latency, but relaxes the guarantee to at least once. You control this execution behavior using triggers. You can set a processing time trigger to kick off micro-batches at fixed intervals, or use the Available Now trigger, which processes all pending data and stops, which is incredibly useful for cost-saving daily batch jobs on streaming infrastructure. We also have asynchronous progress tracking, which checkpoints progress in parallel to data processing, further reducing microbatch latency. Here we see the decision tree for Spark's execution engines. When you configure your trigger type, you dictate the path. The top path is the default microbatch engine, giving you around 100 milliseconds of latency paired with a strict exactly once guarantee. The bottom path represents the continuous processing mode, dropping latency down to just 1 millisecond, but yielding an at least once guarantee. You simply choose the path that best aligns with your business SLAs. To build accurate real-time systems, we must understand the difference between event time and processing time. Processing time is just the wall clock time when Spark happens to receive the data. But event time is the actual timestamp embedded inside the data itself, the exact moment an IoT device recorded a temperature or a user clicked a button. Operating on event time is critical because networks are unpredictable and data arrives out of order. Structured streaming handles this elegantly. It treats event time as just another column in your table. This means you can create time-based aggregations like counting errors every 5 minutes using simple tumbling or sliding window grouping functions. Even better, if an event from 12 12:04 p.m. gets delayed by network lag and arrives at 12:11 p.m. Spark naturally routes it to the correct 12:00 to 12:10 window and updates the partial aggregate. This sequence diagram shows the magic of event time processing. First, event A happens at 12:04 and arrives on time. Spark correctly updates the 12:00 to 12:10 window. But look at event B. It occurred at 12:08, but due to a network hiccup, it arrives late at 12:12. Because Spark relies on event time, it doesn't mistakenly place it in the 12:10 to 12:20 window. Instead, it reaches back and correctly updates the older 12:00 to 12:10 aggregate. This ensures your analytics remain completely accurate. Let's take a deep dive into state management. If Spark is constantly listening for late data to update older windows, it has to keep the intermediate state of those windows in memory. If left unchecked for days, this unbounded state will cause your cluster to crash with an out-of-memory error. To solve this, we use watermarking. A watermark is a dynamic threshold that tells Spark exactly how late data is allowed to be. For example, if you set a watermark of 10 minutes, Spark tracks the maximum event time it has seen. Any window that falls more than 10 minutes behind this maximum event time is finalized, and its state is completely cleared from memory. Late data arriving after the watermark is simply dropped. To implement this, you just chain the dot with watermark function right before your group by clause. It's a simple line of code that ensures your application can run continuously for years without crashing. Follow the logic in this diagram to see how watermarking protects your cluster. Spark constantly observes the maximum event time, let's say 12:30. Given a 10-minute delay setting, the current watermark is calculated as 12:20. Spark evaluates all open windows against this threshold. Windows ending after 12:20 are kept in memory to accept late data. However, any window ending at or before 12:20 is deemed finalized. Its state is safely cleared from memory, freeing up resources, and its final counts are written to the sink. Once Spark has processed the streaming data, it needs to write it to a destination, known as a sink. How it writes that data is determined by the output mode. There are 3 modes you must master. First is append mode. Here, Spark only writes completely new rows to the output. If you are doing aggregations, append mode strictly requires a watermark, because it will only output a Windows result after it is finalized and will never change. Second is update mode. This acts like an upsert. Spark only outputs the specific rows that were updated or added since the last microbatch. Finally, complete mode outputs the entire result table every single time. You only use complete mode for queries where the aggregate table stays small, like counting total unique users today. You can push these outputs to reliable sinks like Kafka or Delta Lake, or use the for each batch function to write custom logic, like saving to a NoSQL database while tracking batch IDs. This diagram provides a clear visual on output modes. As the internal result table updates, the chosen output mode dictates what actually crosses the network to your external data sink. Append mode acts as an insert-only stream for finalized data. Update mode acts as an upsert, minimizing network traffic to only changed rows. And complete mode takes the heavy-handed approach of writing the entire state every trigger. Choosing the right mode ensures downstream compatibility. Let's apply this to a highly profitable real-world use case, ad monetization. Imagine you have 2 massive data streams. One stream contains ad impressions when an ad is shown to a user. The other stream contains ad clicks. To monetize, you must join these streams together to prove an impression led to a click. The challenge in stream joins is that a click can happen long after an impression, meaning Spark has to buffer past inputs as state. To stop state from growing infinitely, we apply 2 constraints. First, we set watermarks on both streams to handle delayed events. Second, we add a strict event time constraint to the join condition. We tell Spark a click must happen between 0 seconds and exactly 1 hour after the impression. With this constraint, Spark knows it can safely drop any impression older than 1 hour from memory, keeping the job blazingly fast while correlating massive streams. Let's walk through this ad monetization join. Both the impression and click streams flow into the stream join operator. Spark then evaluates our custom time constraints. If a click arrives and matches an impression within the 1 hour window, it outputs a successful match. More importantly, as time moves forward, the constraint logic identifies impressions that have aged past the 1 hour mark and safely purges them from the state store, preventing cluster failure. In our final slide, we must discuss production best practices. When doing complex joins or aggregations, your state can grow to millions of keys. By default, Spark stores this state in JVM memory, which leads to massive garbage collection pauses that kill your microbatch latency. The expert move is to switch the state store provider to RocksDB. RocksDB efficiently manages state using native memory and local disk, bypassing JVM limits entirely. Combine this with changelog checkpointing, which uploads only the delta state changes to HDFS or S3 instead of full snapshots, radically reducing your latency. Keep a close eye on your jobs using programmatic asynchronous APIs or simply calling query.lastProgress to monitor input rates and trigger durations. That wraps up our masterclass on Spark structured streaming. If you want to become a certified data engineering architect, I invite you to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. See you next time. Our final diagram shows the hardened production architecture. Notice that the stateful operator bypasses the JVM heap and writes directly to the RocksDB state store in native memory. RocksDB then utilizes changelog checkpointing to swiftly back up small state deltas to durable storage like HDFS or S3, guaranteeing fault tolerance without the latency hit. Finally, task locality keeps the work pinned to the same executors, ensuring rapid processing across microbatches.